Our project, Smoky Skies, focuses on risk assessment and mitigation strategies for wildfire smoke in high-risk communities located in Southern California. In recent years, wildfires in the United States have increased by over 30% from 1980 to 2020, with California alone experiencing more than 8,000 wildfires in 2020. Wildfire smoke, particularly fine particulate matter, aka PM2.5, poses a significant health risk as it can deeply penetrate the lungs and bloodstream, causing severe respiratory conditions. As shown in this graph, respiratory mortality increases steeply as wildfire-related PM2.5 concentrations increase, and unhealthy levels of PM2.5 can cause up to 10% increase in respiratory death compared to good air quality. Our project focuses on the top 5 high-risk communities in Southern California, assessing both the frequency and severity of wildfire smoke exposure while forecasting its impact on respiratory-related deaths. Our goal is to recommend and implement effective mitigation strategies to reduce health risks in these vulnerable communities. To analyze the risk frequency and severity, we collected data from 4 data sources from 2015 to January 2025 in 3 categories. In the frequency data category, we collected monthly PM2.5 air quality data from the EPA. In the risk frequency and severity category, we collected wildfire data from the CAL FIRE database, which provides the number of acres burned for large fires. And we also collected monthly respiratory mortality data from the CDC Wonder database. For data that categorizes risk and potential outcomes, we collected the U.S. county-level census data such as population and median household income. Based on collected data, we identified the top 5 high-risk counties in Southern California as our target areas for risk analysis, including Los Angeles County, Orange County, Riverside County, San Bernardino County, and San Diego County. The input data ranges from medium to high credibility, as most data comes from credible government agencies, with a few exceptions of missing entries. Here is our model design framework. After collecting and processing data from the 4 data sources, we need to identify the relationship between the wildfire factors and the monthly respiratory deaths. After experimenting with a few regression models such as multilinear regression and XGBoost machine learning model, we decided upon the XGBoost model, which uses gradient boosting on multiple decision trees. Each new tree corrects errors from the previous trees in order to minimize the loss function. XGBoost is highly effective to identify nonlinear relationships in the fragmented dataset where not all months have wildfire data. Once we identify the most significant variables, we want to generate the long-term prediction for the death count. In this case, XGBoost does not automatically consider temporal features such as seasonality and trend and is not suitable for multi-step prediction. Instead, we chose the statistical model SERIMAX, which stands for seasonal ARIMA with exogenous factors, which is more suitable for time series prediction on respiratory death forecasts. The model variables are listed in this table, which includes input variables: acres burned, average monthly PM2.5 level, PM2.5 delay by 1, 2, and 3 months, population, median income, and combination variables, as well as the target variable deaths. Here is the code for building our risk analysis model to analyze the risk of wildfire-associated respiratory mortality in the top 5 high-risk counties in Southern California, which are listed in the County Code Dictionary. The first part of our risk model utilizes XGBoost machine learning algorithm to identify the most significant factors affecting the monthly respiratory deaths. In this code block, the input data includes wildfire size measured by acres burned, average monthly PM2.5 level, and census data such as median income and population. Since XGBoost does not have inherent temporal data handling, I need to add time-based features such as month, year, as well as the time-lagged features in PM2.5 with a 1, 2, and 3-month delay for the model to capture these time-based features. In addition, I also added the interaction terms, which are the combination factors of 2 or more features, such as a mix of PM2.5 and population, and the combination of PM2.5 and median income. I started with building the XGBoost model by converting the dataset to a XGBoost D-matrix data structure for efficient data handling. I also specified the XGBoost model parameters such as the squared error loss function to minimize prediction error, the evaluation of root mean squared error, and the maximum depth of individual decision trees. The learning rate, ETA, is set to 0.1, which is a balanced rate to make each decision tree contribute a moderate amount to the final model prediction. By calling the xgb.cv function, I ran the XGBoost model through cross-validation with 5 folds and 100 boosting rounds. The mean RMSE and standard deviation are calculated after the model run. The best trained model is selected to run prediction on the test set, and the test RMSE is calculated as well. Now I will run the XGBoost model to generate the feature importance graph with corresponding performance measurements. From the feature importance graph, we can see that acres burned from wildfires plays the most significant role in predicting respiratory death count with a F-score of 572, followed by average PM2.5 values with an F-score of 275. The 3-month PM2.5 lagging effect and population size also have a sizable impact. From the performance metric output, we see that XGBoost has a relatively small standard deviation at 11.9 and an improved RMSE at 24.87 compared to the mean RMSE of 30 from the cross-validation. Once we identify the most significant features in acres burned and the average monthly PM2.5, we will generate long-term death predictions, ideally 10 years, using these two exogenous variables to quantify the risk frequency and severity using the SERIMAX stats model. Here, the aggregated data are loaded into the time series data frame, which contains all 5 counties' monthly respiratory deaths, average PM2.5 values, and the sum of the burned acres for the month. In the death forecast function, we include acres burned and average monthly PM2.5 as exogenous variables to build the SERIMAX model with both factors. We also specify the non-seasonal and seasonal components, which are autoregressive, integrated, and moving average, with 12 months as a seasonal period, as we see a clear annual pattern in the respiratory deaths trend. The model fitting takes 100 maximum iterations and uses the BFGS optimization method to minimize the loss function. Once the model is trained, it can start generating forecasts by calling the getForecast function. Here we are generating a 10 years forecast with 120 steps ahead based on the monthly data. The results of mean forecast and 95% confidence intervals with upper bound and lower bound are saved into a data frame. To evaluate the SERIMAX prediction performance, we use the metric MAPE, which stands for mean absolute percentage error, which measures average prediction accuracy in percentage. Usually, a less than 10% MAPE is considered very good performance with relatively small error. The rest of the code is for graphing, including generating trend lines and plotting the existing and forecasted data. Now, I will run the code to generate the 10-year forecast from 2025 to 2035 and plot it on a graph. We can see that the model fitting takes some time. From the performance output, we see that this model has pretty good prediction accuracy on monthly respiratory death with a 9.046% MAPE, which indicates the predicted values are within 9% of the actual values on average. From the prediction plot, we see that the risk frequency follows a clear yearly pattern and the predicted death most closely matches with the actual values from 2015 to January 2025. There are some visible mismatches at the peak values, which may be due to other factors unrelated to wildfires. Meanwhile, these mismatches may also be related to our data and model limitations. For example, the CAL FIRE data didn't have monthly distribution for acres burned. Thus, we assumed Gaussian distribution for burned acres across multiple months. The fire incident data from 2024 to January 2025 also had issues as there were only fire start dates along with acres burned. Thus, we had to assume that the acres burned all happened during the same month of the start dates. For the respiratory death forecast, we see that by 2035, the expected monthly death count would reach 750 with a descending trend which is likely associated with the projected population decline in the future years, while the maximum expected deaths would be close to 1250 per month with a slightly upward trend even among the projected population decline, which presents a concerning health risk associated with wildfire smoke. This graph shows a trend of respiratory deaths from 2015 to January 2025. We can clearly identify an annual pattern in the death frequency, which is consistent across all 5 counties. Los Angeles County is shown to have a much higher death count, which is mostly due to the higher population of over 9 billion compared to the other counties with population sizes of 2 to 3 million. This is consistent with the population factor in the feature importance output from the XGBoost model. To analyze the risk severity, as shown in the risk SERIMAX prediction graph, By 2035, the expected respiratory deaths will reach 750 per month in the top 5 counties and nearly 1250 average monthly deaths in the worst scenario. To quantify the financial loss of health risk associated with wildfire smoke, we use a standard measurement at $10 million per death, which is the value of a statistical life provided by the EPA. As shown in this table, the predicted annual financial loss for the 5 counties will reach $90 billion in the average scenario and a whopping $150 billion in the worst case scenario. With the US population projected to decline, the predicted upper level increase of wildfire related respiratory deaths is an alarming health risk that needs to be mitigated. To mitigate the health risk of wildfire smoke, we evaluated mitigation strategies in 3 categories: behavior change, modifying outcomes, and insurance. For behavior change, our mitigation evaluation indicates controlled burns can significantly reduce wildfire severity and insurance cost, potentially saving nearly $2 billion per year in home insurance premiums for the top 5 high-risk counties in Southern California, as shown in this table. Individual actions such as staying indoors, using HEPA air filters, sealing homes, and wearing N95 respirators can reduce PM2.5 exposure by up to 90%, effectively protecting respiratory health. For modifying outcomes, we evaluated clean air shelters with air filtration systems and remote air quality monitoring with health advisory. The cost benefit for the clean air shelter is strongly favorable, with a financial gain of $9.9 million for just one life saved. It is especially beneficial in disadvantaged communities where individuals can't afford the air purifier and home sealing costs. Clean air shelters combined with remote air quality monitoring and health advisories can further mitigate the severe health impacts of wildfire smoke, as remote monitoring provides real-time air quality coverage and enables prompt responses to wildfire-induced air pollution in high-risk communities. In the insurance category, we evaluated and recommended effective insurance solutions, such as parametric insurance with event-based coverage, risk-based premiums, and health insurance add-ons. As shown in this diagram, parametric insurance payout is based on the predefined event. For example, let's say that the PM2.5 level exceeds 200 micrograms per cubic meter for 48 hours. We see that the parametric insurance eliminates loss assessment overhead with a faster lump sum payout to the policyholder. In this example, $500,000 to the health department. This timely payout can be used for emergency treatment of respiratory conditions and providing protective equipment to vulnerable populations and communities. The net benefit of parametric insurance is significant as demonstrated in the example. With a mere 1% reduction in wildfire-induced respiratory death, that is 1% out of the 750 predicted average monthly deaths in 2035 based on our model forecast, it will save at least 7 lives with a benefit of $70 million in VSL value. Based on our evaluation, a combination of effective mitigation approaches are recommended that involve behavior changes such as controlled burns and individual actions, and modifying outcomes by creating clean air shelters along with remote air quality monitoring, as well as adaptive insurance solutions such as parametric insurance. By implementing these comprehensive strategies, we can significantly reduce the health and economic impacts of wildfire smoke, ultimately building a more resilient and sustainable future for the high-risk communities. The health impact and financial risks of wildfire smoke has become increasingly severe in California, especially within the top 5 high-risk counties located in Southern California. With a variety of mitigation strategies aimed at reducing the risk frequency and severity, we're confident that this critical problem can be largely mitigated with enhanced resilience. Our project offers critical risk analysis and mitigation strategies to protect lives and safeguard public well-being against the growing threat of wildfire smoke.